Hi, in this session we will discuss about the single phase AC circuits, that is the different types of um, AC circuits having a pure resistive component or pure inductive component, how the circuit behaves, that is what is the relationship between voltage and current when the circuit contains only the resistive component, and what will be the power. Similarly, when the circuit having the inductive component, what will be the relationship between voltage and current, and also what will be the power. So these analysis we will be discussing in this session. Okay, let us start with analysis of AC circuit containing pure ohmic resistive component. Okay, so let us take a circuit having only the resistive type component, and we can just show the circuit like this. Here V is nothing but an alternating voltage, and we can express V as Vm sin omega t. This we have seen in the previous classes that the voltage is sinusoidal in nature, and due to this applied alternating voltage, the current flowing through the circuit I is also alternating in nature. Let us see what will be the expression for I here. And when the current flows through the resistor, we know that always there will be an voltage drop. And we will call the voltage drop across the resistor R as VR. And therefore, we can write VR as V is equal to I into R. Substituting the value of V here, we can obtain the expression for I. So let me just substitute the value of V. So V is equal to I into R. It becomes Vm sin omega t is equal to I into R. So let us rearrange this equation, and we can write here the expression for I as Vm by R into sin omega t. So let us take this Vm by R part as Im, maximum value of current. So here Vm by R can be expressed as Im. Therefore, I becomes Im sin omega t. Now, let us just compare the expression for V is equal to Vm sin omega t and equation 3, that is I is equal to Im sin omega t. We can observe here both current and voltages are having the same phase. So look into the sinusoidal component. Here it is sin omega t. Here also it is sin omega t. That is omega t is not changing here. So it means for the AC circuit having the pure resistive component, both current and voltages are in phase. They don't have any phase difference. In phase in the sense the quantities voltage and current having the same frequencies will cross the zero reference value at the same time interval, and they increases in the same direction, or they moves in the same direction and reaching their maximum value at the same time interval. So this is nothing but in phase, and here we have the same voltage diagram for voltage, the waveform for voltage and current we can express like this in figure 1, and also the phasor diagram for voltage and current we can write, which has been expressed in this or which has been shown in figure 2. Okay, now we have to show the voltage and current as in phase in the waveform. So here we have represented the voltage sinusoidally, and also the current we have just represented over here. They both are starting at the same point and they are rising in the same direction. They achieve their maximum value at the same time interval here, and also they become zero at this particular point, that is at the same point. Again it continues the same in other direction. Okay, so this is how we can show the waveform for of in phase behavior of voltage and current. Okay, and the time period is expressed along x-axis here. Okay, now let us represent both voltage and current in phasor diagram or in a vector diagram. So in order to write the vector diagram, we have to take the maximum value of the quantity, that is voltage or current, as a length of each vector. So here we will represent voltage along x-axis because we assume the phase angle of V as 0, and here also the phase angle of I is also 0 because they are in phase. Therefore, let us take OB as the vector representing the voltage, and Vm is the maximum value of voltage. So therefore, OB is the vector we have represented along x-axis and for the voltage, and OA is another vector representing the maximum value of current, and since they are in phase Im and Vm, then we have represented along the same line along the x-axis. Okay, right. Now let us see the power variation, or how we can express the power, what happens to the power for the circuit having the pure resistive component. Instantaneous power. We can express the instantaneous power as the product of instantaneous voltage and instantaneous current. Now let us substitute V and I in this expression. So it becomes V is Vm sin omega t, I is Im sin omega t. Now sin omega t into sin omega t sin square omega t. We know that sin square omega t is 1 minus cos 2 omega t divided by 2. The trigonometric function, let us recall, sin square theta is equal to 1 minus cos 2 theta divided by 2. Therefore, accordingly, we can just replace sin square omega t as 1 minus cos 2 omega t divided by 2. Okay. Let us rearrange this, split this term into two terms, Vm Im by 2 and minus Vm Im by 2 into cos 2 omega t. Okay. Now here we can observe clearly instantaneous power has two terms. One is the constant term Vm Im divided by 2. This is the constant term, first term. And the second term is a fluctuating term, that is Vm Im into cos 2 omega t divided by 2. I repeat, the instantaneous power has two terms. The first term is a constant term Vm Im by 2, and the second term is a fluctuating part, that is Vm Im cos 2 omega t by 2. Okay, and we know that always the average value of the sinusoidal varying component is 0 because the same value will, average value will, mean value will be there for positive as well as negative cycle. They both get cancels. Therefore, the second term average value can be considered as 0. Okay. Or we can also say the average value of the sinusoidal term where the frequency is twice than the applied voltage frequency is always 0. Therefore, the second term will not provide any valuable information since its average value is considered as 0. Therefore, we can neglect the second term. That is, this term can be taken as negligible or 0. Okay. Therefore, the instantaneous power is only Vm Im by 2. Vm Im divided by 2. And we can just split this as, or we can rewrite this as Vm by root 2 and Im by root 2. Vm by root 2 is nothing but RMS value of voltage, Vrms, and Im by root 2 is nothing but an RMS value of current, that is Irms. Therefore, P can be expressed as product of V into I, where V and I are nothing but RMS values of voltages and current. Okay, the instantaneous power for the pure resistive component we can express as V into I, where V and I are nothing but RMS values of voltages and current. We can also write the waveform for the instantaneous power, so which we have shown here. So this the two waveforms which are written with the blue lines, they indicate the current and the voltages. So Vm is the maximum value of current, and the second curve having the lower magnitude or the smaller magnitude represents the waveform for the higher magnitude waveform represents the voltage and lower amplitude waveform represents the current. And here you can just take the expression for power P is V into I, that is the product of V and I. So just simply assume at different intervals the values of V and I, and then we can just say what will be the power here. So at let me just take, okay, let me take the voltage and current at this particular point is 0. Therefore 0 into 0 is 0. So we'll assume current as some, here both are positive. Therefore V into I, let us take current amplitude as 2 and voltage amplitude is also 2. 2 into 2 it becomes 4 here. Therefore we can just represent V like this, and here let us take it is some 4 and 4, so it will be 16, and we can represent the I, and also here it is a double value product, and at this case just you can just see when both current and voltage become 0, power becomes 0, and you just observe in other cycle, that is pi to 2 pi, the value of current and voltages, they are negative, but when we take the product minus V and minus I, it becomes positive. Therefore the power is nothing but positive, it won't be negative. So it is always in one direction. Okay, let us say current and voltage at these 2 points are minus 5 and minus 5 becomes minus 25. So it becomes plus 25. So therefore it is plus 25 here. So this is how the waveform can be represented for the voltage power. Yes. Now let us continue our discussion for the inductive type circuit. Okay. Assume the circuit having a pure inductive component. So we can just rewrite the circuit like this. Let us take L as the self-inductance of this inductive coil, and the applied voltage V as Vm sin omega t. So we can just write the due to self-inductance of the coil, the EMF which is induced can be represented as EL is equal to minus L di by dt. Okay, and negative sign, it indicates that always the induced EMF is equal and opposite to the source. Okay, or we can also say the applied voltage at every instant is equal and opposite to the self-induced EMF. Therefore, the negative sign is being indicated over here. Therefore, V is equal to minus EL, and here we know that V is Vm sin omega t, and minus of EL is minus L into di by dt. We can integrate on both the sides. So here the differentiative component and the integration will be cancelled. So we get I over here, and let us send L to the other side. I is equal to Pm by L integration of sin omega t into dt. So integration of sin omega t is minus cos omega t, or we can also write as minus cos omega t can be written as sin omega t minus pi by 2, or sin omega t minus pi by 2 can be written as minus cos omega t. So here the current becomes maximum when the sinusoidal term is 1, that is when sin of omega t minus pi by 2 is equal to 1, I becomes Im. Therefore we can write Im maximum value of the current as Vm by omega L, or this omega L can be represented as XL, which is nothing but inductive reactance. XL can be called as inductive reactance. So therefore, the expression for I is Im sin omega t minus pi by 2, and just look back to the expression of voltage, which is V is equal to Vm sin omega t. V is equal to Vm sin omega t from equation 1, and from equation 2, I is equal to Im sin omega t minus pi by 2. Just observe the sinusoidal term. What is happening for voltage? The phase value is omega t. And here for the current it is omega t minus pi by 2. So there is a difference in phase of voltage and current. So what we can say here, since it is minus pi by 2, what we can say, current lags the voltage by pi by 2. I repeat, looking into the expression for voltage and current, V is Vm sin omega t and I is Im sin omega t minus pi by 2. So just have a look into these two expressions. Here there is a phase difference. How much phase difference is there? Minus pi by 2. Therefore, what we can say, for current it is minus, therefore current lags the voltage by pi by 2. And we can write the waveform and the phasor diagram indicating the lagging of current compared to voltage. So just like this way we can represent. Let us take the waveforms first. Here we'll take voltage and current along y-axis and the time along x-axis for the waveform diagram, that is we are at figure 1. So here, since the voltage is now having the phase difference of 0, therefore we just start at the 0 reference line and we will write the sinusoidal wave for the voltage. Okay, let me just highlight for this one. And now similarly for the current, it is having the phase difference of minus pi by 2, that is it lags the voltage. Therefore that means after pi by 2 period the current should start, that is instead of starting at 0, the current starts at pi by 2 and it increases, and like this it continues, that is there is a phase difference of pi by 2. So lagging in the sense the voltage starts at reference value and it reaches its maximum value prior to the current. So when the voltage is achieves its maximum value at pi by 2, at that time interval the current starts to raise and it becomes maximum at pi. Therefore, we can just say the time interval of starting the zero reference value and reaching the maximum value, we can see it is 90-degree differences there. Therefore, we can say current lags the voltage by pi by 2. And the same thing we can just diagram or in the phasor diagram. So since V is having the phase value of 0 degree, therefore we can represent the vector along x-axis for voltage, and it is assumed that to have a phase angle of 0, therefore we will represent along x-axis. And since the current lags by minus 90 degree, therefore we have to show minus 90 degree phase shift for V and I. Therefore we will represent the vector for I vertically downwards and having the phase difference of minus 90 degree here. Minus 90 degree or pi by 2. Okay, so this is what the voltage and current relationship for the circuit having pure inductive component. Now let us move on to the instantaneous power. Instantaneous power, we know that P is equal to V into I. Now substituting the value of V in and then I and simplifying, we get the value of P as minus Vm Im sine 2 omega t divided by 2. So here the instantaneous power contains only one term and which is sinusoidal. So we know that whenever the sinusoidal component is considered, its average value is always 0 because it will be having the same average value for positive and then negative cycles. Therefore, its average value is 0 and hence the average power in a pure inductive circuit is assumed to be nothing but 0. The average value in a pure inductive circuit is nothing but 0. We can also verify that mathematically. Okay, from the instantaneous power we can find the average power over a one complete cycle. So over a one complete cycle, let us take the mean value and we can just represent integration of this sinusoidal term over one complete period, that is 0 to 2 pi. That therefore 0 to 2 pi integration of sine 2 omega t divided by its length over one period, that is 1 divided by pi. Okay, so it will be 0. Hence, the average power in a pure inductive circuit is 0. In other way, we can also say the power consumed by the pure inductive component is 0. Okay. That's all. Thank you.